Okay, guys, so in the previous class I taught you the first method to design the state feedback control law, and today I'm gonna teach you an example of that. So for the first method, so we are in the stage of the design and control the state feedback. Suppose, if you remember that we discussed in the previous class, x dot is equal to ax plus bu for the CISO system. I said the A matrix, which is LTI system, is 0, 2, 0, 0, 0, 1, -1, -3, and -4, and the B matrix or vector, because the CISO system going to be 0, 0, and 1. That's right. And your boss asking you to design a feedback control law that has desirable closed loop poles, or the eigenvalues of the system is S1 is -1 plus j, a pair of complex conjugate poles. And as I discussed in the previous class, because we want to have under damp system, like as your car suspension system that has under damp behavior, as I taught in the vibration and on the graduate control courses. And in the previous class I explained why -5 compared to real part of the complex conjugate poles, because it's gonna vanish soon when time goes to infinity. I explained in the previous class. Go and see it on the YouTube. So we're gonna, what we want to do, we want to just design -u is kx. We want to design this. On the other hand, we want to calculate the gain matrix. And after I design, I'm gonna use the MATLAB and I'm gonna simulate in MATLAB. Okay. So first step that I told you in the previous class was that we have to check the controllability of the system. Controllability of the system. How we can do that? By controllability metrics. That's right. Because it's a third order system, controllability metrics gonna be B, AB, remember this is general form, AB square until a n minus 1b. This is controllability metrics. So because n is 3, this is a third order system, this is 3 by 3. That's right. So n minus 1 gonna be 2. So gonna be b here for this problem, ab a square b. So we have the b from here. So ab gonna be what? AB gonna be 3 by 1 again. AB gonna be, look at here, 0, 0, 0, 0, 0, 1, that's right, and 0, 0, -4. We got that. And a square b, which is a in AB, that's right. So gonna be another column vector. So gonna be a multiplied by this 0, 2, 0. So here you're gonna have 2, 0, 0, -4. Here we go, and 0, -3 plus 16. So it's gonna be 13. Here we go. So now the controllability metrics here gonna be what? Here gonna be B 0, 0, 1, AB 0, 1, -4, A square B 2, -4, and 13. So because this is square matrix, I talked with Greek. Because this is a square matrix, the easiest way to calculate the rank of the matrix by hand is to determine the determinant of this matrix, which is going to be 0, 0, and it's going to be 2 multiplied by 0, 1, 1, minus 4. You can do all of these after graduation by MATLAB. That's right. Or in MATLAB, as I taught you, you can insert this matrix and say rank of M. So, but this is I'm teaching you. So this rank of this matrix. So the determinant of this matrix is going to be -2, which is not 0 for this matrix. So the rank of this controllability matrix, as I taught you several times, gonna be 3. So hence you can say this system is controllable. So step 1, as I mentioned in the previous class, done. Okay, so the second step that I told you in the previous class for designing the gain matrix was, is it recording? Yeah, was what? You have to find the eigenvalues of the system or the polynomial or characteristic equation. I taught you why characteristic equation and eigenvalue problem are the same in the control domain. That's right, with this proof. So Si minus A. So Si minus A, because 3 by 3 gonna be S0 0 0 S0 0 0. I is identity matrix. S minus A. Your A is what? Your A is 0 2 1 0 0 1 minus 1 minus 3 and minus 4. That's right. The determinant of this. So this is called the determinant of what? Finally, S, right, -2 and S -2. Oh, here is 0. Your original A. Why don't say S1? See, 2 0 2. So and 0 0 S and -1, and here gonna be +1 minus 3, and here you're gonna have S plus 4. Bingo, determinant of this. That's right. Let me double check the numbers. Right. So determinant of this is very easy. Gonna be S in the cofactors of this S -1 3 S plus 4. That's right. +2 in 0 -1 1 S plus 4, right? And this is 0. So what you get gonna be S multiplied by S plus 4 plus 3 is there, plus 2 in plus 1 is equal to 0. So let me change the color for happiness. So what we're gonna, this is S in S square plus 4S plus 3 plus 2 is 0. Finally, what we get is this polynomial from the previous class. Remember, we are giving us A's. Gonna be S cubed plus 4S square plus 3S plus 2 is 0. And you have to compare with the general things that I told you. Gonna be S3 plus A1 S square plus A2S plus A3 is 0. Because remember, this system is third order system, so you're gonna have S3 here. Understand? So comparing this, you get A1 is 4, A2 is 3, and A3 is 2. So we're going to use that in the gain matrix. Clear? Remember from the previous class? So the then in the third step, I said you have to find, remember third step, you have to find the transformation matrix T, which is equal to controllability matrix by W. But first you have to check if your state space equations, state space equations are already in the form of controllable canonical form. If it is, I said that the transformation matrix is identity matrix. Remember? Hold on. I taught you in the first class. If you remember, you can go to your notes. Controllable canonical form is in this form. X dot 1 until x dot n, you have in the first class notes, is for the LTI system is 0 1 0 dot 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 0 0 0 1 dot 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 0, finally comes on here 0 0 0 1 minus an minus 1, and finally minus a1. That's right. So x1 xn plus b is this. Obviously, comparing your A with your original example third order system, it says that your system is not, look at here, is not in controllable canonical form. So you have to calculate T as MW. And I said W is what? And I said W based on the ANs that you found is like this: AN minus 1, AN minus 2 until A1, then AN minus 2 comes down here to 1, 0, and then this comes down, and then A1 finally 0 and 0, and finally you're gonna have 1 0 and 0. So based on whatever we found here, look at here. So your AN minus 1 is this. Your NS3 AN minus 1, sorry, your AN minus 1 is this, AN minus 1, because your N is 3, N is 3, third order system, 3 minus 1, 2. Your AN minus 2 is what? Is this AN minus 2. And this is your what? This is your AN. Understand? So what you're gonna do based on, see? So let me change the color. So your W gonna be AN minus 1, AN1 minus 2. Get here. AN minus 1, 3, AN minus 2, 4. 3, 4, and finally 1. Here we go. Understand? 1. Then what is the rest? am minus 2 1 0. What is am minus 2? Am minus 2 gonna be 4 4 1 0. That's right. And 1 0, and finally the last line gonna be 1 0 0 1 0 0. Here we go. So your T transformation matrix, your transformation matrix T gonna be M. We calculated M. What is M? M is this 0 0 2 0 1 minus 4. It is 0 0 2. That's right. 0 1 minus 4. Here we go. Controllability matrix. 1 minus 4 13. 1 minus 4 and 13 multiplied by W. 3 4 1 4 1 0 1 0 0. Here we go. So the result is the transformation matrix that we're going to use in the gain matrix going to be 0 0 2 0 0 0 0 0 0 0 4 minus 4 gonna be 0 0 1 0 0 0 0 3 okay, 3 minus 16 13 13 plus 3 16 minus 4 16 0 4 minus 4 0 1 0 0. This is your transformation matrix. We just calculated that. That's right. What are we going to use in the gain matrix? So we have that. Then, as I said before, right? As I said before in the previous class, you have to make, as step 4, you have to make this polynomial, desirable poles or eigenvalues of the system. You have 3, so you have to make like this. So, what are those? So, your desirable that your boss asks you is under damped system. These are, you have to put there. You're gonna have plus 1 minus j, plus 1 plus j. That's right, because I is changing the sign. And what? And what? And s plus 5. Because we're gonna, by these polynomial, we're gonna generate alpha i's. Remember from the previous class? So let us do that. So this is gonna be 1 by 1. This is gonna be s square. That's right. Plus 2s, because you know that from linear algebra, a minus a in s plus a gonna be finally what? Forget about this. Okay, so Let me do one because you're gonna ask me how you did it. So on the other hand, it's gonna be s square plus, right? Plus s multiplied by 1 plus j plus s squared in 1 plus minus j plus 1 minus j in 1 plus j. That's right. In s plus 5 is 0. See, s squared, s in this plus s in this, and plus these two together. That's right. And these are like that. Okay, so what's the result of that? The result of that is equal to, again, s squared plus, look at here, this minus ajs plus j, so remaining out of this term gonna be 2s plus 2s, and now multiplication of these two terms, right? These two terms gonna be 1 plus 1 minus j squared. It's gonna be 1 minus j squared. What is j squared? Is minus 1, so minus 1, it is 2. So the result of this is gonna be 2. Here we go, plus 2. That's right, in s plus 5. This is algebra, trivial algebra. So this is gonna be s cubed plus 2s squared plus 2s plus 5s squared plus 10s plus 10. And finally what you get is s cubed plus 7s squared, this and this, plus 12s plus 10 is 0. Now you have to compare this with whatever I gave you in the previous class. S cubed plus alpha 1 s squared plus alpha 2s plus alpha 3 is 0. So is trivial comparison. Alpha 1 is 7, right? Alpha 2 is 12 and alpha 3 is 10. Understand? Bingo. Now, based on whatever I taught in the class, the gain matrix gonna be alpha 3 minus A3 that we found, alpha 2 minus A2 that we found, alpha 1 minus A1 that we found in transfer matrix inverse. So alpha 3 is 10. What is A3? Is 2. So it's gonna be 10 minus 2. Alpha 2 is 12. What is A2? Is 3. It's gonna be 12 minus 3. Alpha 1 is 7. What is A1? Is 4. So it is 7 minus 4 in transformation matrix of inverse of that. What is transformation matrix? We found that. Here we go. Inverse of this. Inverse of this. So inverse of 2 0 0 0 1 0 0 0 1. Inverse of this. Clear, guys? So if you calculate that even by MATLAB, I'm just skipping here because we can do by MATLAB. Okay, so let us do that. Let me show you. It's recording. Yeah. So if I do that by MATLAB, oh, it comes up. Okay. So what was that? It is 8. Got here, guys. It is 8, 9, 3 multiplied by inverse of this. Okay. 8, 9, 3. Got here, guys. So you can say the gain is 8, 9, 3, 1 by 3. That's right. 8, 9, 3 in inverse of that matrix. Matrix was 2, 0, 0. The next line is 0, 1, 0. That's right. And the next line is 0 transformation matrix 1. Here we go. That's right. So this is the answer. So the gain matrix is 4, 9, 3. So you see that just simply by MATLAB. Inverse of that matrix 4, 9, 3. Whereas this is 1 by 3 multiplied by 3 by 3. Result is 1 by 3. So the gain matrix, because your system is third order system, so the gain matrix that you get is how much? 4, 9, and 3. Bingo! You just designed a state feedback controller, which u gonna be minus kx. Or if I write in MATLAB in the code, as you will see now, you're gonna have your u is minus 4, 9, 3 in x, because you have 3 state variables. You have third order system. Here we go. This is your input to the system. Why? Because to return it to the origin. Return it to origin. Understand? Okay. So let me try this in MATLAB. See the controller that I designed, how it works. So first of all, let me write it here first. First of all, before going to MATLAB, if this is your LTI system, x.x plus pu, on the other hand, look at here, your x.1 is how much? Look at here, is how much? Is 2 x2. Because this is like this, guys, let me not like that. x.1, x.2, x.3. That's right. I want that you visualize what you are doing. Is equal to your a is 0. What is your a in the system? 2, 0, 0, 0, 1, minus 1, minus 3, and minus 4. Ax state variable x1, x2, x3 plus bu CISO system 0, 0, 1 in u, and we just designed u. That's right. So on the other hand, if I simplify this, x.1 is equal to how much? 0, 2 x2, 0. x.2 is equal to how much? 0, 0 x3 plus 0, and x.3 is how much? Is minus x1 minus 3 x2 minus 4 x3 plus u. Understand? So when you go to MATLAB, first we have to develop OD in MATLAB, right? So let us do that together. We have time. So MATLAB, you're gonna put a new script and file, as I taught you, function in the undergraduate control vibration function, say dm is equal to state feedback, I say time and the state variable m. Instead of x1, x2, x3, I'm putting m here. Okay, then you have to say dm or dx is zeros. How many state variables we have? We have 3, so 1 and 3 to open the initial space for that. Okay, so then as I said, the m1 or the x1 is equal to how much? Look at here, 2x2. This is 2 in m2. dm2 is how much, if I'm not wrong? Is x3 is m3, and dm3 is what? dm3 is minus x1 minus 3x2 minus is minus m1 minus 3m2 minus 4m3 plus u. This is the controller that you design. First of all, let me run this LTI system by saying that there is no control input for the system first. There's no controller. And I'm going to save it here as MS696. And oh, hold on, guys. I have to connect to. Must be SF. Okay. So see, this is SF. They have both the same name. Then I'm going to say T and Y, the output of the system, as you know, is ODE is equal to, this is the general format in MATLAB. ODE, I'm saying format, hold on, guys. Okay, so ODE45, one of the solvers I taught you several times in STSU. So, and at, oh no, ODE45, oh, I'm getting old. ODE45, then at what? SF. Go and call, at in MATLAB means go and call the SFM file. SF, and then from time of 0 with time step of 0.1 to 10, and initial you have 3 state variables, because we went back to the origin. I'm saying from 1 minus 1.5 and 0.5. These are the initial conditions. Remember that I was talking about initial condition of x1, initial condition of x2, initial condition of x3. Here we go. So then I'm saying that SF solver, okay, in MS696. Do you have the same folder? Let me double check. This is SF solver. Where's SF? They have to be. Oh, I mistakenly saved on that folder. Okay. So let me open it from here because yeah. Okay. So SF. Okay. Then I'm gonna plot this without any controller. Figure 1. Plot total time, that is 10 seconds. Look at like here. Look at here, guys. 10 seconds. 10 seconds. Okay. And then x1 gonna be y. All the rows, and the first one I'm gonna x1. I'm gonna say plot in blue. Okay. So let me see how it looks like. Hopefully there is no change. Oh, there's a typo here, guys. We don't have 4, 3. Okay, so you're gonna have. Oops. What happens? Counter. Am I getting over? Hold on. Oh, sorry guys, I had a typo here. This must be 3 and 1. Okay, not 1 and 3. I have 2 state variables. Okay. This command gives you, look at here. This command gives you 3. So this is the vectors, not 1 and 2. I had the typo here. So if I run this, I'm gonna increase it to 20. Okay. If I run this, you see that x3 after 15 seconds backs to what? This. So if I let me do this. Figure 1, figure 2, and figure 3. I'm gonna put 2 x3. I'm gonna make this red and black. Look at here. Here we go. See, after 15 seconds, eventually they go to 3. So what we have done, see, this is x2, this is x1. Now what we have done, we said, now these look at here guys, these are the transient I want to look at it after 15 seconds and a huge overshoot. This happens, that's right. Look at here, huge overshoot. Okay, so we said that your boss said that you want to have a controller. The controller is minus k. K was we calculate as 493, 493 multiplied by what? M1, that's right, M2, right, and M3. First of all, let me go to this. First of all, as you see here, this is 1 by 3, this is 3 by 1. So you're gonna have a scalar here. Understand? 3 by 3, you're gonna have one scalar. This is not one scalar. Okay. So because this must go inside here, one number. Understand what I'm talking about? So now exactly I said minus k that we calculated. K, this is gain matrix in state variables in 1 and 2. Okay, I'm saving that. Now if I do that, 493, let me double check. Yeah, if I do that, let's see how the responses behaves. Oh, see, in the previous case it was going to the origin, as I said, to 0 after 15 seconds here, and with a huge overshoot. Now here much smoother and goes to the origin in the 5 seconds because of a pair of complex conjugate poles or under damped system. That's right. The same here, 5 seconds and more smoothly, and here. Understand? If I want to compare this with the previous case, it's easy. How it's easy? You're gonna say this is a trick. Get here, guys. You can plot in the same. It's gonna be M4, the same equations. M5, M5, M6, M6, gonna be M4, M5, M6, and say U1. And I say again the original equation, U1 is 0, has no controller. But here you have 6 state variables. So you're gonna have 6. Okay? You understand what I'm talking about? And then hopefully it works. Yeah. M5, M5, M6, M4, M5, M6, U1. And then you have to change here everything, because this is for the same initial conditions, because you have 6 state variables. Here we go. Now we can say compare them. See? Hold on. See? x1 with x4 and change the color red. Then hold on, look at here. Again, I'm putting everything blue to compare controlled version with uncontrolled version. This is gonna be with 5 and this is gonna be with 6 and so, and again this is blue. So blue are for controlled system and the reds are for uncontrolled system. U1 is 0 or U is 0, but here we have U here. Okay, understand? So hopefully I didn't make a mistake. Okay, let us run it. Yep. Okay, so blue R for the control system goes to the origin much fast. That's right. This is for X3. Okay, and the red R for our uncontrolled system. You see that it takes to 15 seconds. Understand? So we modify the transient response of the system. Again, blue R is for the control system, goes at almost 5 seconds. And the red one is for uncontrolled system in 15 seconds. This is X2. And the X1, blue is for the control system. After 5 seconds goes to origin. And this takes much uncontrolled system. So we modified transient response of the system by state feedback control law. State feedback control law. Okay, but I promised you that you have to plot the phase plane. So mean that you have to plot velocity versus position. So you have to do this, guys. But here I'm going to just plot one of them. XY. This is the X1. This is X2. Control system, uncontrolled system. Because I want to give you how to back to origin. Look at here, guys. Here we go. Okay, let me close this. Okay, here we go. See, here is the X. This is X dot. Understand what I'm talking about? Just giving you. So starting from the same initial conditions, the blue line is for the control line goes to origin 0 and 0, much faster than the uncontrolled system red line, much faster than that. So this is how I was showing you. For betting visualization, you have to put the grid command. See, here we go. Okay, here we go. See, 0 and 0. So we designed the controller. So this topics continue because we have two methods for the state feedback. Then I will go to observability, and then the non-zero reference input can be step input, and then the optimality and the LQR system. So this continues.